Hey, this is Dr. B, and in this lecture, let's talk about the background chemistry that you need to understand nuclear medicine. I use the term chemistry lightly because we're really going to be talking about nuclear rather than chemical processes. Remember that a nuclear process involves a change to the nucleus. A chemical process is one in which the nucleus is not changed, but new substances are formed. So nuclear medicine, in order to perform it, you're going to need unstable nuclei. These can lead to either detection or they can be used themselves as an energetic substance. So we use them for medical visualization as well as treatment. And let's begin with just basic understanding of the atom. Most people are familiar with the concept that the atom has protons and neutrons in the nucleus and electrons outside the nucleus. Those substances are not all considered to be elementary particles, meaning they can be broken down into simpler substances. Now we're talking about a nuclear, not an electronic, not a chemical level. So the electron is considered to be an elementary particle of matter, meaning it can no longer be further broken down. However, protons and neutrons are composed of quarks and gluons. Now, quarks are considered to be matter particles, meaning fermions. Gluons are believed to be force particles, meaning energy. And the standard model consists of 12 different matter particles and 5 different force particles. That's going a little deeper than we need to, but that's fine. These unstable nuclei that we will use in medicinal chemistry are called radionuclides. They may have an excess number of neutrons, but not always. That means the neutron to proton ratio will be greater than 1.5. It's always true that if you're above atomic number 83, meaning any element with more than 83 protons, all of the isotopes of all of those elements are unstable, and they are radionuclides. Interestingly, atomic number 43 also has no stable isotopes. Technetium does not exist naturally. It falls apart too quickly. And when these things fall apart, they give rise to various nuclear decay particles. Here's a list of them. They can give rise to an alpha particle. This is a helium nucleus. That means it has no electrons. 2 plus implies that both of the electrons in the helium atom are gone. And otherwise, it's pretty much garden variety helium. It has the 2 protons that it must have, so its atomic number is 2. It also has 2 neutrons in this particular isotope, and that's not uncommon at all. This is the atomic number, the number of protons. This is the mass number, protons plus neutrons. Very common form of nuclear decay, an alpha particle. This is a beta particle. We use the negative sign to show that it's making a garden variety electron, but we have some rather unusual symbols here. These make sense mathematically when you understand that a beta particle involves a neutron decaying into a proton and an electron and a form of energy known as an antineutrino. I put this here because I found that this can be obscure enough that I need to read it directly. That's beta decay. We use the minus sign to show that it involves an electron, a regular electron. There's also gamma decay. This is simply energy being given off in the form of a gamma particle, you could say. I mean, energy does consist of discrete particles. They're not matter, but we still call them particles. So that's gamma decay. You can also have beta plus decay. This is also known as positron decay, and I'll read it directly. So positron emission, also known as beta plus decay, it involves protons inside the nucleus, an unstable one, being converted into neutrons, positrons, and neutrinos. Note that that's a little bit different than here. In beta minus decay, a neutron decays into a proton, an electron, and an antineutrino. Pretty obscure stuff, and we wouldn't be teaching it at all if we didn't have to talk about positron emission tomography. And here it is. That's a positron right there. Here's something pretty simple. This is just a neutron. No protons, one neutron. That's neutron decay. And here's proton decay. One proton, no neutrons, proton emission. We can summarize it like this. If a proton's being injected, that's simply proton emission. It's rather rare. If a neutron is being ejected, well, it's pretty easy to understand. That usually occurs during fission, which means that things are breaking down. The nucleus is fragmenting into smaller particles, and oftentimes it also gives off neutrons. Interestingly, those can accelerate a nuclear fission process. Think of them as the gas pedal. There's also substances that absorb neutrons. Those can slow down a nuclear fission process, which is important if you live near a nuclear fission reactor like I do. There's one nearby in Waterford, Connecticut, and if it's not controlled, it can lead to a meltdown. Here we have a neutron being converted into a proton, an electron, and an antineutrino. We call this beta emission. Sometimes you see the negative sign. Here we have positron emission, which is given the beta plus emission sign, where a proton is converted into a neutron, a positron, and a neutrino. Alpha emission is perhaps the most common. This is helium-2+. And you can also simply give off energy in the form of gamma energy. This is gamma emission. Those are the major types of nuclear decay. Regardless of the type of decay, we can measure its rate. It's got to be equal to some constant times its concentration. Low number would mean a fast decay. Low number would mean a slow decay. A big number would mean a fast decay. And without showing you the math, we can demonstrate that the half-life, the time for half of one of these radionuclides to decay, will be equal to 0.693 divided by K, K being the rate constant. If you take a look at a rates unit in chemistry, you'll see that all nuclear decay is first order and obeys this sort of a formula. Okay, that's an introduction to the background material for understanding nuclear medicine.